Hi folks, in this video we're going to look at the variance of discrete random variables. We'll take a look at various examples. This is material from chapter 12 of our textbook. So the overview is three different examples. The first I call basic variance. Here we're calculating variance just from the definition. The second one is based on some properties of variance that everybody should know. And the third is an application involving expected cost. And again, all problems are from chapter 12. Okay, so let's just say we have a simple discrete random variable x. You can see x takes on these three values, and these are the probabilities. Whenever we have one of these distributions, we should check to see that it adds up to 1. So I get 49.581. Okay, so the probabilities are good. And let's say we're interested in finding, well, e of x, the variance of x. This is just sort of an intermediate step. And something a little different, the expectation of x squared minus 4x. All right, so the first is pretty straightforward. We're just looking at the sum of the products, x times its probability. So we can multiply these out and then simplify, and you should see that we get 15.36. And again, I always like to think about my answer and just say, well, it should be roughly the middle. It's sort of a weighted average. So I have 1, 3, 27, 31. We're getting 15. So it is somewhere in the middle. The weights make it move back and forth a little bit, but it is a certain type of an average. Okay, to find e of x squared, right? Remember, we need e of x squared when we find the variance, because the variance is going to be e of x squared minus the expectation squared. So the difference between e of x and e of x squared is that we square these x values. So you can see it's a very similar calculation, but these first values, the x values are squared. So we square them all, and then we multiply out, add up the products. So you should get 396.12. All right, but remember that's not the variance. If you want to call it anything, that's the second moment. But we'll talk about moments later on in the course. The variance now is equal to e of x squared, so 396.12, minus the expectation, 15.36 squared. So if we simplify this out, you should find that we get 160.1904. Okay, the last part is to find e of x squared minus 4x. You could almost think of this as the expectation of a sum, and it is true. I think I mentioned it in previous video. The expectation of a sum is a sum of the expectations. So we can break this up and find e of x squared. So e of x squared is 396.12, and then just minus 4 times e of x. So minus 4 times 15.36. And if we just simply multiply this out, do the subtraction, we get 334.68. Okay, so again, pretty generic, right? It's nice to start with the generic problems before we move on to some of the more advanced items. All right, in the next example, we're going to take advantage of some properties of expected value and variance, right? I just mentioned one, the expectation of a sum, so the sum of the expectations. Okay, what can we say about variance and some of the related expectations that we need? Well, if we have two random variables, if we have x and y, and if they're independent, then we could say the expectation of the product is the product of the expectations. Okay, but this depends on independence, right? That other item I was talking about, expectation of a sum, does not depend on independence. It's always true. But here, if I have x and y independent, then we get this very nice property. And this can be generalized a little bit. Instead of x and y, I can have a function of x. And h may be a function of y. So the expectation of this product is the product of the expectations. Okay, so that's another good property. All right, another important property of variation, okay, is if I have some sort of, let's just call it a linear combination. X is a random variable. Think of A and B as just some real numbers, constants. Then if we want the variance of ax plus b, we get a squared times the variance of x. Okay, and notice that sort of the b term disappears. Okay, this can be proved. I believe there's a proof of this in the lecture notes, certainly in the book. So the main idea is if you have a random variable and you add b to all the values of a random variable, that doesn't affect the variance. Okay, so we have to remember two things here. When you take the a out, it gets squared, and the b sort of disappears. All right, so that's useful for some calculations. And then the last property that I will mention here is sort of what you get when you put some of these things together. If I have n random variables, I have x1, x2, and so on up to xn, and they're all independent, and I have constants a1 up through an, so these might be just real numbers, then the variance of this sum is equal to a1 squared times the variance of x1 plus it would be a2 squared times the variance of x2 and so on up to an squared variance of xn. So you can see we're sort of applying this property over and over again. It's almost like if you had to prove this, we could use induction together with this property and get a formal proof of that. All right, we're going to do something different here. We're going to take a look at now an example that uses a couple of these properties. Let's suppose I have x and y are independent, and I know a couple of things. I know the variance of x is 6, e of x squared y squared is 150, e of y is 2, e of x is 2, and I want the variance of y. Right? I want the variance of y. So, how do we go about this? Well, first of all, let's think about the variance of x. What do we know? Well, on the one hand, we know the variance of x is 6. Right? This was a given condition. On the other hand, we know this equation, right? Sometimes I call this the shortcut formula. It's not the definition, so it is something that's sort of easier than the definition. the variance is 6. Let's leave e of x squared. But I know e of x is 2, right? That's given up here. So this is 2 squared. And you could see that you could easily solve for e of x squared. Right? 2 squared is 4. Add 4 to the other side. So I get e of x squared is 10. All right, well, that helps because I know here that e of x squared times y squared is 150. I could separate this out, right? Why could I separate this out? Because I know I have independence, right? So we have e of x squared y squared is equal to e of x squared times e of y squared. So that's 150. So there I'm just using the independence and what's given. And what else do I know? I'm using another fact here somewhere. We get e of y squared is equal to 15. Why do we know that? Well, if I look up here, I have e of x squared, right? So I could take this term right here and replace it by 10. So I have 10 e of y squared is 150. Divide through by 10, and I get e of y squared is 15. So over here I say from the previous 2 lines. You can see this works a lot like a proof. This is almost like a proof, even though this is the unknown. I'm putting this together really the same way you would a proof. All right, so finally, what can we say here, right? Remember, we want the variance of y. We know e of y squared, and we know e of y is 2. So we could put those 2 facts together. 15 minus 2 squared, so 15 minus 4 is 11, and we have it, the variance of y. Okay, in our next problem, I call this an application of variance. It's just sort of using variance in a practical way for some sort of, really essentially it's an expected cost problem. So let's say that X represents the number of smoke alarms in an apartment. And we could sort of narrow, the thinking here. Maybe these are all apartments on Long Island, let's say. From government data, you find the mass, or we call this also the PMF, the mass of X, the probability mass function. So X varies from 0 to 5. That would be a lot of smoke alarms in one apartment, but it happens. As you can see here, not too often, 5% of the time. Okay, so here we have our probability mass function, probability distribution. It's called either of those. Now, assume each alarm requires 1 battery per year, and batteries cost $2.35. So we want to know 2 things. What's the expected cost in batteries for smoke alarms for a randomly selected apartment? And what's the variance of cost? So right now, I'm going to suggest that you turn off or stop the video and try to find, well, at least try to find e of x and the variance of x, right? That's not going to give you the complete answer, but it's going to take you a long way. So find e of x and the variance, excuse me, of x. All right, did you get that e of x is 2.4? And if I fast forward a little bit, down here, variance of x is 1.34. Okay, if you did, excellent. Now, we want to convert this to expected cost. All right, this is the expectation of X. But remember, X is the number of smoke detectors in an apartment. Okay, we want to use that and try to figure out an average cost. Okay, but that's not difficult. Um, we figure out that there's 2.4 smoke alarms in an apartment. So the average cost is simply $2.35 times 2.4, or $5.64. So that's like the expected cost. All right, so from the expected number of smoke alarms, we find the expected cost. Now, let's say we wanted to know the variance of the cost. So we can go ahead and find the variance of X. So we find E of X squared, 7.1. Use this formula. I just see right now there should be a square right here. E of X squared minus the expectation squared. I do have it here though. 7.1 minus 2.4 squared works out to be 1.34. So to get the variance of the cost, we take 235 and we have to square that times 1.34. So here we're using a property, the variance, really we're looking at the variance of 235 times x. So we take the 235 out, multiply by 1.34, and we get 740. Okay, I hope you've enjoyed this video. Then we've reached the end.